Hello everyone, today I will be talking about TESS, a very small space telescope that is about to be launched on a seemingly oversized rocket and will probably yield a gigantic amount of data. Now, the reason why I'm talking about TESS today is of course because it is going to be launched today in a few hours after uploading this video. If you're watching this video later, you can of course rewatch the launch. I will live stream it, I will also record it, so you can watch all the versions later. However, for now I'll be talking about TESS itself, its purpose, its design, and then about the rocket it is launching on, and why it isn't quite as much overkill as it might seem at first. Now, TESS is short for Transiting Exoplanet Survey Satellite, which kinda already tells you what it is going to do. This space telescope is designed a little bit different from others. It might not even quite classify as a space telescope. It's more of a massive workhorse. It will be in a very high Earth orbit and observe many stars, many nearby stars, but it will actually survey the entire sky, and that is a first. It's the first space telescope with a rather wide field of view that will actually make a full survey of the entire sky in a relatively short amount of time, and also survey the entire sky over a stretch of time so that each star will be watched for a longer period of time. And that comes back to one of the two main methods of detecting exoplanets, and I have made a video about exoplanets and how we find them before, and I was back then ending on the James Webb Space Telescope that might eventually finally be launched and will somewhat continue the work of TESS. However, TESS is not so much a precision instrument. I mean, it is a scientific instrument. It is built to some standard of precision much higher than any consumer goods, but compared to other space telescopes, it doesn't have a very high resolution, it doesn't have a very precise spectrometer or anything like that. It's really more of a really high quality digital camera with a large field of view that is relatively small and maneuverable. And what it will do is track the brightness of different stars over a stretch of time, and it can measure the brightness to quite a bit of accuracy. And if there are any dips in brightness on a regular interval, then we can conclude that there might be planets going around that star. By the interval between those dips, we can conclude the orbital parameters of that planet, and if there are several planets. Of course, this only works if the planets also pass between us and that star, so we actually know that this method can only find statistically some 2% or so of all planets that exist, because that are the chances of a planet randomly being aligned with us. However, since it is a relatively sensitive method that works relatively well with relatively normal instruments and can find relatively small planets around relatively far away stars with enough precision to confirm them, this method still accounts for more than half of all exoplanets we have found so far, and TESS is going to use that method for a very wide survey. It knows that it can't find all planets, because not all planets actually pass between their star and us, but it can find a lot more planets than we have found today. Statistically, we expect about 20,000 exoplanets to be found by TESS, of which then statistically around 1,000 might be relatively Earth-like or Earth-similar planets of a roughly Earth-sized, in the habitable zone, rocky planets. While the mission will survey all of the sky, it will have some additional focus. It will basically image some part of the sky more frequently than others, as its images kind of overlap, and those are actually precisely planned to be those parts of the sky where we have a higher chance of detecting planets with the transit method, since we to some degree know the historical or astronomical relation between our solar system and other stars and the physics behind it. We can expect that the chances of a planet being aligned so that it can pass between its star and us are slightly higher in some sections of the sky than in others, and it will focus on these sections. Now, its data might also bring some other use, but its main purpose is clearly to find more exoplanets faster than any other space telescope could, and then allow other space telescopes to focus on these interesting points that it found. Most space telescopes have much more detailed and precise instruments, but they can only view a very small section of the sky, even if you move them around over a long time. They only image a tiny section of night sky, and so this relatively simple small space telescope might still add a lot of information and allow us to better adjust other space telescopes. Now, if we look at the actual spacecraft itself, it is pretty tiny. Its weight might be normal for interplanetary probes, but for orbital satellites or space telescopes, it's a really small device. Well, for once, it doesn't need to be bigger, and in space you don't build any heavier than you have to. This thing only weighs 350 kilograms, and it's a bit surprising that it launches on a Falcon 9, because the Falcon 9 can launch up to 20 tons into low Earth orbit and more than 3 tons onto escape velocity, but there are a few things to keep in mind. For once, the Falcon 9 will not be used in expendable mode. It will not land back at the Cape either, it will land on a drone ship, but that still means it has less performance than its listed maximum performance on SpaceX website. And secondly, its target orbit is not low Earth orbit or geostationary orbit. Its target orbit is actually most comparable to a lunar transfer orbit. It's close to escape velocity. Now, it's not a lunar transfer orbit, it's slightly below that, and it's not aligned that it would actually match up with the Moon in terms of transfer window, but the Falcon 9's target orbit will deliver TESS into a orbit with a perigee in low Earth orbit and an apogee at 270,000 kilometers, which is not quite but close to the Moon's orbit and far beyond geostationary orbit. So it will need a lot more delta V than it would for a geostationary orbit. So with that, the Falcon 9 is still a little bit overkill, but only by a tiny factor, and given that the Falcon 9 is simply so much more practical and cheap nowadays compared to other rockets of its performance, now this was initially planned to launch on a Delta II, but they revised that plan, and it turns out that the Falcon 9 is simply so efficient that it's cheaper than a slightly smaller rocket that wouldn't be overkill, but it's less efficient, so it would still be more expensive. Now, TESS, after being delivered on that transfer orbit, will do a few orbital maneuvers itself, but those need relatively little delta V. Once you are close to the Moon's orbit in those really high areas, orbital velocity by capitalist laws becomes very small, so these are very low delta V maneuvers. It also uses a lunar gravity assist maneuver to slightly boost up its orbit. Its orbit will not become circular, its orbit will stay highly elliptical, and it will basically be a 1 to 2 lunar cyclo orbit. Now, knowing that, we could use fancy orbital mechanics to calculate what the eccentricity of any factor 2 cyclo orbit will be, and it's 0.55, which also matches up with the listed orbital parameters that are listed as TESS target orbit. What that essentially means is that it will have an apogee of 375,000 kilometers, which is basically within the range of the Moon's orbit between its perigee and apogee, and a perigee of 108,000 kilometers, which is much lower and makes the orbit highly elliptical, but most importantly reduces its semi-major axis and thus its orbital period, and exactly by a factor of 2. That means its orbital period is half the orbital period of the Moon, basically half a month, and its apogee dips within the Moon's orbit, but it will be offset by 90 degrees, and obviously since its orbital period is half that of the Moon will, between two of its orbits, switch by 180 degrees, and then will be 90 degrees to the opposite side. What that means is that the tidal forces of the Moon affecting TESS's orbit will even out between these two cycles, and thus will keep TESS's orbit exactly the same and stabilize it against other forces. Now, you can see this in the visualization. I made a Kerbal Space Program replica / preview of its orbital mechanics. Now, that is slightly simplified, since there I just adjusted the orbit using the RCS thruster I built into the replica without using a lunar flyby and several cycles, but the final orbit is the same, although adjusted for the Kerbal system, and you can kind of see the point there. It's visualized to the point where you can probably kind of easily understand what I mean. Now, Kerbal doesn't simulate tidal forces, but the effect will be basically the same, since the point is that these tidal forces even out over one orbit and the next, and they're relatively small anyways, so the whole point of this orbital optimization is to keep the effect of tidal forces as small as possible. Now with that, I will end this little overview over TESS. I might go a little deeper into this specific matter later in another video if you're interested. Although before that, I would like to make another physics and theory video and go a bit into SpaceX and BFR updates. This is really just a current event occasion video. Of course, if you have any questions about spaceflight, aviation or physics, I'm always open for requests. With that, I will end this video, and we will hopefully be able to see the launch live in a few hours. It is set for 22:30 GMT with a 30-second launch window. There is a slight weather risk, so it might be delayed, but that is relatively unlikely, so most likely it will just launch today. So see you live, and as always, thanks for watching.